Please let me know if you cannot hear me. So let me get started. This is the presentation that I have today. If you cannot hear me or you don't see my screen, please let me know because I am just looking at the full screen.
Oh, you're good, Mr. Tintas. We can see
Thank
you
you.
and hear you.
Thank you so much. So this week we're covering enumeration systems, place value systems, and base systems. And we're also going to talk about prime numbers. This is a continuation from studying the ancient numerations. Last Friday, we talked about the Babylonian, Egyptian, Mayan, and especially the Mayans and the Babylonian had place values. So now we're going to continue with that, but we're going to do it in different bases. This is what we would call it the modern number systems. The regular number system is called Hindu Arabic, and this is base 10. And in this system, we actually have the symbols 0, 1, 2, 3, 4. So these are our digits, or more properly called, they're called numerals. And the place value, these are powers of 10. And notice that starting from the right, this is what we call the place of the ones. Let me see if I can put a one in there. So because any number to the power 0 equals 1. So this is the place of the ones. And then we have 10 to the power 1, which is just 10. Any number to the power 1 is itself. 10 squared, this is the hundreds, the thousands, which is cube. Fourths, this is 10,000s, and 100,000s. And we're going to be doing different bases, not just base 10, because different bases are typically used. For example, if you are an electrician or if you're in computer science, the base 2 is a very common one where we use zeros and 1. In fact, we are used to that in computer science. We know that a lot of the algorithms of the computer are done in binary. So base 5 has symbols 0, 1, 2, 3, 4, and you're not allowed to use any other digit greater than 5. And the place values are going to start again with the ones. And then since it's base 5, the next one is going to be 5 to the power 1 on the left, which is 5. And then 5 squared, which is 25, 5 to the power 3, which is 125, and so on. Base 2, as I mentioned before, this is the binary one. And the place values are, starting on the right, we have the place of the units or ones, and then 2s, 4s, 8s, and so on. Notice that that means that as we want to write down larger values, we keep using more digits to the left. And more digits to the left typically imply that you have a bigger number. So the first thing that I'm going to do is make a conversion. So I want to convert, this number is in base 5. Notice it's a little bit small, so I'm going to rewrite it. I have 2, 3, 1, 4, and we write down the base below, base 5. I know my students told me during class if they needed to write down the 5 every single time. And my suggestion would be, if you have different bases, it is needed, because I could use exactly the same symbols, the same digits, 2, 3, 1, 4. And if it's in base 3, it represents a different number. But if I guess every example has a different base. So within that example, if you don't write it down, just remember that the base is 5. So to answer this, to know what this number is in base 5, I'm going to write down the number in expanded form. And to write it in expanded form, we need to know the place values, which is, again, anytime that you're using a base, you're going to start with the ones, which is 5 to the power 0. And it doesn't matter what the base is. Any number to the power 0 is always going to be 1. So this was 1, and then 5, 25, and 125. Notice that I only need those place values because my number, which is 2 to the power 3, I'm sorry, 2314 base 5, there's no powers in this. It only uses 4 digits. So this would be in the ones or the place of the ones. This is the fives. This is the 25s. And the place value of these two is 125. So on the expansion, what I'm going to do is I'm going to multiply each symbol or each digit by its by its so each digit by the place value. So starting on the right, on the rightmost number, which is 4, this is in the place of the 1, so it'll be 4 times 5 to the power 0, which is going to be 4 times 1. And then 1 times 5 to the power 1, because we're in base 5. 3 times 5 squared, and then 2 times 5 to the power 3. And then, so I next remember to use PEMDAS. So even though PEMDAS says to start with parentheses, and I wrote parentheses, you want to start inside the parentheses is like a new problem. So if I look at the parentheses on the left, let me highlight it. I have 2 times 5 to the power 3. So within the parentheses is like a brand new problem. So I got to start on the exponent. And do not confuse it. Remember that the powers means to multiply the number 3 times. Whatever the exponent is, you multiply it by itself. So this is a 5. So multiply 5 3 times, which is 5 times 5 times 5. Often when you're doing these problems very quickly, it's common to just simply multiply 5 times 3, but that wouldn't give you the correct power. This is actually 125 if you do it in your calculator. So notice that below I wrote down 2 times 125 because the 2 is on the place of the 5 to the power 3. So it's going to be 2 times the value of the power, and then plus, and I do the same thing on each parenthesis, 3 times 25, 1 times 5, and 4 times 0, which is, not 0, 4 times 5 to the power 0, which is 1. So 4 times 1, it'll be 4. And this is my simplification. So 2 times 125, that is 250. 3 times 25, this is 75. 5 and 4. So do the sum of all of these numbers, 250 plus 75 plus 5 plus 4, and I got as an answer 334. So this means that this numeral or this number in base 5, 2314 base 5, is equivalent to 334 in base 10, like the regular number. So I would say regular. So anytime that you see numbers that have a base, they don't have the normal value that they have. You actually need to do the expansion to find out what is the equivalent in a regular, what's the equivalent in base 10, or as we called it last week, Hindu Arabic numbers. Let's do another example. So the next example is convert 315. I cannot even read it as 3,156 because that way of reading numbers is actually only when you have it on base 10. If it's on a different base, then it's best just to say 3156 base 7. So I want to know what this is equivalent in regular numbers. Well, because my base is 7, the place values are going to use powers of 7. Starting on the right-hand side, 7 to the power 0, 7 to the power 1, 7 squared, and 7 to the power 3. Notice that I only need these ones, but if I had, let's say that this number was actually larger. If I had 3, 1, 5, 6, 7, but maybe more digits to the left, like 2, 5. Notice that I cannot use anything greater or equal to 7 because the symbols or the numerals in base 7 are only 0, 1, 2, 3, 4, 5, 6. That's the largest digit that I can use in a number in base 7. So maybe one more, a 1. So this is a number that has 1, 2, 3, 4, 5, 6, 7, 7 digits. And these will require more of these powers. So this is the place of the ones. Oh, I'm so sorry. It changed my slide automatically. Let me go back to presenting mode. Here you go. So the 6 would be the place of 7 to the power 0, which is always the ones or the units. And then this is 7 to the power 1. This one is 7 squared, which is exactly what I'm doing here, huh? 7 squared. And then the 3 is 7 to the power 3. The 2 would be 7 to the power 4. The 5 would be 7 to the power 5. And the 1, 7 to the power 6. So often when I do these problems, I only write down some of the powers, but you're going to need as many as digits on your numeral or on your number. So for this example, remember the expansion form has the powers and the digits. So from the right is going to be 6 times 7 to the power 0 plus 5 times 7 to the power 1, 1 times 7 squared, and 3 times 7 cubed. Next, we're going to do our powers. Within each parenthesis, you want to do the powers first. So 7 to the power 3 is 343. 7 squared is going to be 49. 7 to the power 1 is 7. And any number to the power 0 is 1. If you're doing this in your calculator, I always recommend my students to have a scientific calculator because it makes it easier. But if you're doing this on your cell phone or if you have any other calculator, you need to learn how to type the powers on your own calculator. I wouldn't recommend to get used to the cell phone because we don't allow cell phones during exams or quizzes. So it's best to learn how to do this. Or you could always do the multiplications by hand, but I always tell my students, if you're doing everything by hand, you're taking time that you could be using in another problem. And I want to mention in most calculators, even your cell phone, if you're using your cell phone right now, to do the power, often you need to do one of these keys. So you would do 7, you type the base, and then there's often a key which is written xy, x to the power y, or it could be just together like xy. And then you put the 3, and often that multiplies 7 times 7 times 7 times 7, which is 343. Another way of typing this in your calculator would be this symbol. Some people call it the caret symbol. I learned to call that the hat symbol. To me, it's like a hat. And so this also means power. So 7 to the power 3 is 343. And if you don't have, if you don't see any of those symbols or you don't want to get confused, you could just remember that the powers multiply the base the amount of times of the exponent. So I suppose you could always multiply 7 times 7 times 7, and that also give you the 343. Okay, so that was just kind of like a quick note if you're doing this in a calculator, and just to find out what is the symbol that your calculator uses for exponents so you don't confuse them. All right, so after we've done exponents in PEMDAS, the next thing would be multiplication. So now we gotta multiply all of these numbers. 303 times 343, which is 1,029, 1 times 49, 5 times 7, and 6 times 1. Add up all of the numbers, and we get our final answer of 1,119. So this numeral 3156, oh, sorry, 7, or we could just call it a number in base 7. This number in base 7 is equivalent in regular numbers that for us in our usual numbers, we would call it 1119. And if I change the base, 3156, let's say that the base now would be 8, then that would be something else. That's why I do encourage that you write down the word below, the placement of this word, like right under the number, would be called an index or a subscript. And I recommend that you write it down because it indicates the base so that you can find what is the equivalent in regular numbers, which is base 10. Let's take a look now at one more example of these type of problems, like converting a number in a different base into regular base, Hindu Arabic numbers. And this is a binary number. Binary is something that we do quite often because the binaries, like I mentioned, are very common in computer science. This is how computers work. And I would challenge you all to maybe find out, in my classes, I always tell students, find out some of the applications, some of the interesting things about these different type of numbers. And something that would be very interesting is how the calculator what does a 1 and a 0 represents, not in a well, maybe in the calculator as well, but specifically in a computer. How is it we're used to hearing the computer uses binary to process all of the algorithms? What I would ask you to find out how does it represent a 0 and a 1, and how does he use it to do all of the functions that we could do with the calculator, with the computer. Okay, so this is a pretty lengthy number. It has a lot of digits. And because it's base 10, the first thing that I did is put my bases. So starting on the right, 2 to the power 0, 2 to the power 1, 2 to the power 2, and so on. And how many digits do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So I need the same amount of powers. Because I'm starting on 0, I'm going to go all the way till 8. So it'll be 0, 1, 2, 3, 4, 5, 6, 7, 8. Because if you include the 0, that makes a total of 9 places. Okay. Now notice that on the answer, this answer actually is cut off. Let me see if I can wait this. Let me redo. Well, it is everything in here. It's not really cut off. It's just it just went from started here and it ended from here. It kind of like goes this way and it ends over here. So starting from the right, it's gonna be 1 times 2 to the power 0, and then 0 times 2 to the power 1, 1, 2 to the power square, and then do the next 3 digits, or the next 3 powers are multiplied by 0. So 1, 2, and 3, the one that is below. And then I get to the 1, the first one on the right. Well, I would say the third to the last number. And this is 1, 2 to the power 6, plus the second to the last is 1 times 2 to the power 7, and the very last one on the left is 1 times 2 to the power 8. So to find the answer, do all of your powers. 2 to the power 0 is actually just 1. 2 to the power 2 is 2, 4, 8, 16, 32, 64. That's actually the numbers that you see in pink. Those are the powers: 64, 128, and 256. 2 to the power 1 is actually 2, but if you multiply it by 0, it's going to give you 0 at the end. So often, something that I do is that when the digit is a 0, I don't even include it in the calculation. So this, since it's going to give me a 0 in the end, it's not going to contribute to the sum. The next one is 2 squared, which is 4. 4 times 1 is just 4. And so this is not going to contribute, not going to contribute, not going to contribute. 2 to the power 6 is 64 times 1. That's just a 64. And we could see it here. Another 1 times 2 to the power 7, because 1 is the largest symbol. Remember that in base 2, you can only use 0 and 1. because you're not allowed to use the same number as the base, and it has to be from 0 all the way till 1. Well, that's just 2 zeros and 1s. So anytime if you have a 0, it's not going to contribute, it'll cancel. And if you have a 1, then that's just the power. So numbers in binary, they're just really representing a sum of powers of 2. So 2 to the power 7 is just 128. And that's what I wrote here. 2 to the power 8 is 256. And then this is, where are my 3 zeros? Well, I have a total of 4 zeros in the numeral. So let's just count it. 1, 2, 3, 4. So those are the zeros. And the other numbers that are not zeros are 256, which is counted, 128, 64. I have a 4. This is my 4. And the very first one, which is a 1. So if you do this sum, 4 plus 1 plus 64 plus 128 plus 256, the final result would be 453. Okay, so this is the last example for converting a number that is into a different base into base 10. Now, the next thing that I want to do is I want to do it, well, I do have one more. Sorry. I do have one more because, so you could have numbers in bases, which could be base 5, base 6, base 7, base 8, base 9. Base 10, 11, and then as soon as you get to larger bases, such as 12, you need numerals that are letters. So the symbols that you're allowed to write here, and I think I actually have them on the slide. Symbols or numerals in base 12 would be the digits from 0 to 9. And we don't use the 10 because we want to use a symbol or numeral that is only one thing, like one digit. So after 9, we start using letters, A, B, C, D, E, F. And the letter means the next value. So after 9, A has the value of 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So using these, so when you look at my numeral is A5B. So this is a number in base 12. What is the equivalent in regular numbers? Well, the way that I've solved all of this problem is by doing the expansion of the number. So I'm going to do the expansion. Remember that to expand it, we're going to need the powers of the base. So starting on the right, it'll be 12 to the power 0, which is whatever the base, that's always 1, so the place of the ones. The next place value is 12 to the power 1, the 12s, 12 squared, 12 cubed, and so on. So that. If you have more digits, then you include more powers. I actually only have 1, 2, 3 digits, so I really only needed 3 powers. Okay, so now let's do the expansion. So the expansion is multiply each digit by its place value or its power. So B times 12 to the power 0, 5 times 12 to the power 1, A times 12 to the power squared. And now I do in this example, I just wrote the final answer. I did everything at the same time. I did the power, which is 12 squared is 144. And then I replaced the letter A with its value, which is 10. So A times 12 squared is equivalent to 10 times 144. Next, I do 5 times 12, which is 60. And the digit of the ones or the units is B times 1, which is 11 times 1. So multiply, follow your PEMDAS, do the multiplication, 1,440, 60, and 11. Add up all those 3 numbers, and your final answer would be 1,511. So this number in base 12 is equivalent to 1,511 in regular Hindu Arabic numbers. Keep in mind that these digits are used, actually I wrote all the way until the F, but if it's base 12, remember that we cut it, like you're not allowed to use the actual 12, so you go one below, which is 11, which is the letter B. So you can use any digit from 0 to 9 all the way until B. If it was base 13, then I would include the C. Base 14, I would include the D. Base 15, I include the E. And all the 15 symbols or numerals, all of these 15 ones, this would be for base 16, which we call hexadecimal. And hexadecimal bases is another base that also computers and calculators use to make computations. So binary and hexadecimal are pretty famous. They're pretty popular because their applications are in computer science. Okay, so as I mentioned before, I wanted to do some examples where now I have a regular number in base 10 and I want to convert it into one of these bases. So I have this number which is 5,821 and I want to convert it to base 3 and also to base 16. So it's two different exercises, A and B. On A, I'm going to convert the same number in base 3 and then on B, the same number to base 16. Now, when we're doing conversions into these bases, we got to do it exactly how we did it when we covered the Babylonians and the Mayan. So when we cover that section, you're supposed to do divisions, like you're dividing different times. So in the same way, I'm gonna do divisions, and you could start by dividing by because it's base 3. We could start by dividing by 3. This is kind of like a shortcut. There's actually different ways of doing this. Perhaps the more intuitive way would be to write down all of the powers of 3, which are so it would be like 3 to the power 0, 3 to the power 1, 3 squared, 3 to the power 3, power 4, and that's actually too many. I didn't need that many. I only have 4 digits, so I only needed up to 3 to the power 3. And then find that, well, actually, that's not right. I do need more because I'm not doing an expansion. I am actually converting into the base, into that. So the most intuitive way would be to find out all of these powers, but they're equal, and then find the largest power that fits into that. And then you divide. And you just continue that process, repeating divisions. Well, what I'm going to show you, the answer it's in there's a specific way that we organize all of these divisions, because you could have a lot of divisions all over your paper and it's a little bit disorganized. So one way of doing these divisions is start by dividing by the base. So my number was 5,821 divided by 3. And then if you do this division by hand, I kind of skipped the whole thing, but that's how you would set it up if you're doing it by hand. You have the division symbol, and then you put the 3 outside. And I just skip all of the steps in between, but the final answer is 1,940, and the remainder is 1. So the remainder is what it is here at the end. The way that you can do this in the calculator, because the calculator actually shows you the decimal. In fact, let me do it on my calculator. So 5821 divided by 3 would give me 1,940.3333, and there's a bunch of 3s. So what you're gonna do is you could use your calculator to find these numbers. You select the whole number, so don't include the decimal point, don't include the digit, the decimal point. Anything to the right, do not include it, just the whole number, the integer number. And we call that the quotient. So we put the quotient right below, which is 1,940. Now you multiply 3 times 1,940, which is the one that I have in green, 5,820. And now you subtract it, and that gives you the remainder. So that's a way of skipping the whole division by hand so that you can find these numbers, the one on the top, which we call the quotient. I often call this the result of the division, but we also need the remainders. In fact, it is the remainders what is gonna give us the final answer. But as you notice on the table that I started right here, I'm gonna need actually both the quotient and the remainder. So I put my number on the top, and then I put 3 to the left, and then I put a line, and I put like these 3 columns to separate. So I'm always dividing by 3. So my next step would be put a 3 here, and I'm gonna divide 1,940 and divide it by 3. And I'll put the result here, which is the quotient, and I'll put the remainder over here. So I did it again on my calculator. Let me write down the calculations. So if you do this in a calculator, you could set it up like divide 646 by 3, and it gives me, of course, well, it gives not, of course. Now I'm actually getting ahead. Sorry, I'm supposed to be dividing. I wanted to show you how I got those two numbers. So it's 1,940 divided by 3, which is 646. Then multiply again. It gave me other digits. It was 646.6666, but I only took the 646. What that means is that the 3 only fits 646 evenly, like completely. And then there's like a port that then you cannot add an extra 3. And so what is the remainder? To find the remainder, now multiply 646 times 3. That will give you 1,938. Subtract them, and the remainder is 2, which I already have it in there, huh? And I continue this process until I no longer can divide by 3. So the next step would be divide by 3. And I'm going to put the quotient here, and I'm going to put the remainder over there. And I believe at this point, I just skip everything. And I just put all of the results as is shown in the book. So notice this is the table that I'm constructing here. And so after 646, you get 215, 71, 23, 7. And then when you divide these, when you divide 7 by 3, if it's 2 times and the remainder is 1, and you stop there because 3 does not fit anymore. Now, if you notice at the shape of the arrow, to write down the number in base 3, you're going to start from the one on the left and go all the way to the top. So you're following the direction of the arrow. So because my last number to the left is a 2, so it'll be 2. And then next you have a 1. Then I have 1, 2, 3 2s, 2, 2, 2, 1. So you write down the 1, 2, and the 1 on the top, that's on the place of the units. And then this is base 3. Because then again, and this is what my students were telling me, like, hey, do I need to put base 3 all the time? Well, if you don't get it confused, but technically, if I write all of these digits again, 2, 1, 2, 2, 1, 2, 1, and I change the base, let's say base 4, these are actually not equal. This is a different number. This represents 5,821. If I do it in base 4, this represents something else. So it is a good habit to write down the base so that we know exactly what is. So if you put the base, then we can convert it back into base 10 so that we find the original value, 5,820. I suppose if you don't put the base, then it may not be clear. Well, if you don't put the base, we usually assume that it is base 10. So I would assume all of that is in base 10. This would be 21,222,121. Okay, so that was the answer for base 3. Exactly the same process I would do to do base 16. So to do base 16, I would start by dividing my number by 16. And then if it's 363 times, that's my quotient. And then I multiply these two in my calculator, and it gives me 5,808. I subtract them, and then I get the remainder, which is 13. In base 16, you can actually have a remainder that has 2 digits because 16 is larger than 13 and it doesn't fit anymore, to simplify it. And remember that if you're in base 16, the one that we call hexadecimal, after the 9, you have the symbols A, B, C, D, E, and F. So this 13, I would convert it to the letter D. So my numeral or my digit is going to be D because D is equivalent to 13. And I just continue the process. Now I put 3 in here. I should have put 16, huh? My divisors are the base. I divide it by 16. And so I do it one more time, divide this by 16, and I put the quotient, I put it here, and then I put the remainder. Let me do it just one more time. So 3, and I'll do it by hand, like doing the house symbol of the division. 363, you put the 16 outside. So 363 divided by 16, it gives me 22. And then to find the remainder, multiply these two, 16 times 22, which is 352. And then you get a remainder of 11. And so I'm going to put the 22 here, and 11, which is equivalent to the letter B. So the next numeral would be B. And then continue like that. Actually, there's only one more, huh? Divide by 16. Well, that only fits once. And then that's it, because I can, well, I do need to find the remainder. So 22 divided by 16, if it's 1, so 22 minus 16 would be 6. So I have a remainder of 6. So my numeral, starting from the bottom number, and remember that I have an arrow that goes like that, would be that one, 1, 6, B, D, and then base 16. Base 16. I think I had the whole diagram, which is right here. And that's exactly what I had, huh? 1, 6, 8. Well, actually, this is supposed to be B, because there's a typo here, B. So the numeral is 1, 6, B, D, base 16. Okay. So now we've covered how to convert numbers into both. You can have it on a different base, and you can write it in the regular basis, which is base 10, the Hindu Arabic numbers. Have a Hindu Arabic number in a regular number, base 10. You could put it into any other base. You could put it into base 3, base 16, base 8, base 5, whatever you just. What you're gonna do is you're gonna do divisions by the base, and then the remainders are gonna give you the numerals, are gonna give you the symbols that you need to express the number in that base. Okay, so one last example, the double-double method. This is a method that can be used to convert only binary. So if you have a number in binary, which is this number, on my example. 1, 1. Let me make sure that I copy this correctly. I believe I did. One way that you can find, and I probably should have left the spaces between the digits. So you're gonna start with the 1 on the left, and then you move to the right. If you encounter a 0, you multiply it by 2, so times 2. So starting with 1, your initial value is gonna be 1. If you find a 0 to the right, you multiply it by 2, so if 0 times 2. And then if you find a 1, you multiply it by 2 plus 1. So it's kind of like operations that we do as we're moving to the right. So starting with the 1 on the left is going to be our initial value. So 1 times 2 is actually going to be 2. And then I move to the next one, which is a 1. So these 2, I'm going to multiply it by 2 and add a 1. So 2 times 2 plus 1 is going to give me 4 plus 1, which is 5. So up to this point, now I have a 5. Now I move to the next one, and it's another 1. So I multiply by 2 and add a 1. Since I had a 5, so that's going to be 5 times 2 is 10 plus 1, 11. There. And then the next one, I encounter a 0, so I'm just going to multiply it by 2. So that's going to give me now 22. And then another 0, so multiply it by 2. 22 times 2, so times 2 and times 2. That is 44. And the last one, the last one on the right, my last digit, since it is a 1, I'm going to apply the procedure where you multiply by 2 and then you add a 1. So if you multiply 44 by 2, that's going to give you 88 plus the 1 is 89. And so this number in base 2 is equivalent to 89. So this is a procedure that is called the double, and it can only be used when you have binary to convert it into Hindu Arabic or like regular numbers. Okay, so this concludes the conversions. Now, of course, something that we want to do when we have numbers is we want to be able to use them to make a lot of calculations. So that's what we call arithmetic. And arithmetic usually consists of addition, subtraction, multiplication. So how would I add numbers in different bases? These kind of like helps us understand how do we add numbers in our regular basis. So notice that I have my sum. It says find the sum of 1, 1, 1, 1, 0 in base 2 and 1, 0, 1, 1 base 2. So you set up this is a sum or addition. So you set it up in the regular way. Start with the units of the ones and align them. So you write down all of your digits and then the other one below aligning on the ones. And then from there on, they should be aligned. So on the top number, I'm going to add the 0 and the 1. And then the next, it's like I have like columns or place values. The next place value are ones. And then I continue like that. So we're matching the numbers by place values. Then I'm going to add 0 plus 1. Well, this is a 1. And then on the next, I got to add 1 plus 1. But 1 plus 1 is actually 2. But remember that in binary, I'm not allowed to write down any symbol that is greater than or equal than 2. So in binary, I can only use 0 and 1. So what I do in my class is that I write down some of the numbers in binary. So 0 has the value of 0. 1 has the value of 1. 2 has the value of, well, in order to write 2 in binary, I'm actually going to write it as 1, 0. Because this is a 0 on the ones, and this 1 is on the place. Remember that the place values, this is the ones, and this is 2 to the power 1, which is 2. So having 1, 2, and 0, 1, so that makes 2 times 1 plus 0, which is just 2. And so just because 2 is equal to 1, 0 in base 2, I'm going to write down the digit of the symbol of the units. I put the 0 and I carry the 1. So I carry the 1. And now I move on to the next place value, and I'm going to have 1 plus 1 plus 0. That's another 2. So I'm going to have 1, 0. So put the 0 and carry the 1 to the left. You carried it on to the next place value. On the next column, or the next place value, I have 1 plus 1 plus 1. That is 3. A 3 in binary is actually written as 1, 1. Because this would mean that you have 1, 2, and 1, 1. And if you add them, 2 plus 1, you get 3. So 3 is 1, 1 in base 2. So you're going to write down the 1 on the units. You put the 1 here and carry the other one on the left. And now I have 1, 1, which it's a 1 plus 1. Now I add them here, which is a 2. And we know that 2 is 1, 0. So I put there's nothing else to add. So I assume that there's a 0 below. So I put the digit of the units, or the ones. I put it here. And then I could carry the 1 on the other side, but there's nothing to add. So it's like adding 0. So I could just put it there. So my final answer when you add these two numbers is going to be all of these, 1, 0, 1, 0, 0, 1 in base 2. This is very similar to what we do in base 10, but I feel like when we do it in base 10, it's kind of like not clear as to what we're doing or why we're doing that. Let's do one more example. So you could add as many numerals or as many numbers as you want. So this is 2, 5 in base 6 plus 3, 2 in base 6 plus 4, 2 in base 6. So it's we could say it's a sum of 3 numbers, 3 numerals. And of course, when you're adding, you could put them in any order. Remember that when you're adding, and if you have all plus signs only, like if all of your signs are plus, that is our addition or sum, the order in which you write down those numbers doesn't matter. So even when you're setting up the sum, you could put the 25 on the top, then 32 and 42 at the end. Or you could put the 32 on the top, the 42 in the middle, or you could put it in a different way. The answer should be the same. So let's do our sum. So I'm going to start on the ones. Let me separate by doing kind of like a line, my place values. So I'm going to add 5 plus 2 plus 2. Like and this is just like regular digits, 5 plus 2 plus 2, that actually would give me 9. But this is in base 6. So I need to write down the 9 in base 6. So let's write down some of the numbers in base 6. Well, base 6 allows digits from 0 all the way until you get to 5, like one less of the base. And then starting with this, you need one more place value. You need another digit. So 6 is actually 1, 0. And this is what I was talking about at the beginning, that the 1, 0 could represent many things. It's not going to be a regular 10. So this is the number 6 in base 6, because it's having a 0 on the ones and having a 1 on the 6. So 6 plus 0, that will give me 6 already. 7 is going to be, let me put it here. It's equivalent to 6. And then 7 is going to be 1, 1. 8 is going to be 1, 2, because I'm allowed to use the digit 2. Think about it like the one on the left represents the 6. So I have 1 6 plus a 1, that makes 7. 1 6 plus a 2, I got 8. So the next, which is 9, would be 1 and 3. Let me put the index, the base. So 9 is actually 1 3. So since my sum gave me a 1 3, I'm gonna put the 3, the digit of the units below, and I'm gonna carry the 1 into the next place value. And then I do the whole sum. So that's gonna be 1 plus 2 plus 3 plus 4. And I'm gonna add this in the regular way. 1 plus 2 plus 3 plus 4, this is 10. And now I gotta write down 10 in base 6. So 10 in base 6 is actually 1 4. And if you remember when we do addition in regular numbers, you could just put since there's no more place values, then you could just put the whole thing in that order. Or if you want to do the whole process, you could create a new place value. You put the 4, carry the 1, but then that 1 drops all the way. So this sum is equivalent to 143 in base 6. Okay, so we're done. We have done sums. The next natural thing to do would be to subtract. The subtraction has the numbers. Now, when we do addition, we always carry, because when we get 2 digits, we carry the next one into the next place value. So that operation that I was just doing, that was called a carry. When I'm doing subtraction, I am actually going to borrow. Not always. We borrow exactly when you're subtracting a larger number from a smaller one. Like in this example, the first thing that is, I'm going to set it up, aligning the place values. So the 3 aligns with the 4, the 6 with the 2, and the 4 with the 1. Notice that when we subtract, it's like the bottom number from the top one. So I could do 2 minus 6, I could do 1 minus 4, but on the units, I kind of have a problem because 4 is actually larger. I have 3 minus 4. So what we do is we borrow from the next place value. So this 5, we borrow 1, so this reduces by 1 unit and it becomes a 5. But because it's on the place of the 7s, remember that the place values were 1, 7, 7 squared, 7 to the power 3. We're in base 7, so since we're in the 7s, borrowing 1 from here means that you're adding 7, so plus 7. So on the right, I'm gonna add 7 plus 3, which makes it a 10. And now I can subtract. 10 minus 4 is gonna give me 6, which this is a digit that is allowed in base 7, so 6. And then on the next place value, since I borrow 1, I'm not gonna use the 6, I'm gonna use the 5. 5 minus 2, this is actually 3. And 4 minus 1, this is 3. So my answer is 336 in base 7. Let me see if I have one more example for this. No, I'm actually gonna move on to the multiplication. And since I'm getting close to the end of today's hour, then this is probably gonna be my last example. So the multiplication, let's set it up the regular way, which is, I usually like when we do this in base 10, when we learn this in elementary or middle school, you would start by putting I like to put the number with the most digits on top. So I'm gonna put 1, 2, 3, and then base 4. And I like to put the number with the smaller amount of digits below. And then this is a multiplication. And I'm gonna follow kind of like the same procedure that we do. I just need to be converting it all the time into base 4. So I multiply 3 times 3, so that gives me 9. But I gotta write down 9 in base 4. So 9 in base 4 is actually 2 and a 1. Because to get a 9 in base 4, I actually need two 4s. Remember that this is the place of the 4s and this is the place of the 1s. So 4 times 2 will make 8 plus 1, 9. And I put the 1 below and I carry the other one on here and I'm going to add it after multiplying. So then I use my 3 and I multiply 3 times 2. So it's 3 times 2, which is 6. But because I had this extra 2 that I carry, so 6 plus 2 makes it an 8. Now I need to write down 8 in base 4. 8 in base 4 is going to be, I need a 6. I'm sorry, I actually it's two 4s, right? Two 4s and a 0. So 2, 0 is actually 8. Because if I have 2 times 4, that already gives me 8. So unlike before, I'm going to write down the 0 and I carry the 2 on the other place value. And I multiply one more time, 3 times 1, which is 3, plus the 2 that I carry, so plus 2, that's 3 plus 2, it makes it a 5. And 5 in base 2 is 1, 1 in base 4. Sorry, I keep confusing my bases. Because if I have 1, 4 and 1, 1, 4 plus 1 would give me 5. So, and at this point, I could just put both of them because even if I were to carry it onto the next place value, there's nothing to multiply. So it's like I will multiply 3 times 0 plus 1 is just 1. So we might as well just put both of them at the very end. And this is my answer. When we multiply 3 times 123, well, 3 base 4 times 123 base 4, we get 1101 in base 4. Okay, so I think this is a good time to stop here. I didn't get to the prime numbers, so in the next video, we're gonna cover prime numbers. You'll have a good Friday. Enjoy the rest of your Friday. And this is all for me. I give it back to our host.
Thank you so much, Mr. Tintos, for your wonderful presentation. We do want to remind you all about our previously recorded sessions, which are available on a YouTube playlist. The session will also be available on that playlist later today. And before you all leave, I want to share the TVE sessions that we will have next. At 1 p.m. today, we will have a presentation on CSD with John Estrada and the Writing Center with Vanessa Zuniga. We will be back next week at 11 a.m., where Math 1332 will cover the Exam 3 review, and Math 2412 will cover sequences, series, mathematical induction, and binomial theorem. Our 1 p.m. session next week will be a presentation on victim advocacy with Isela Grael. Thank you all for coming in today. We hope you all have a lovely weekend. If you have any questions, feel free to use the chat box or your mic. We hope to see everyone again for Happy Math Hour.